Good afternoon, students. The last class we discussed about the equivalent circuit of a single phase transformer. That is, we have to determine the shunt branch parameters R0, X0, and also series branch parameters R01, X01, as well as R02, X02. That may be depending upon the equivalent parameters referred to the primary or equivalent circuit parameters referred to the secondary. You have to draw the equivalent circuit of a single phase transformer referred to the primary. That is nothing but approximation of the approximation equivalent circuit of a single phase transformer. Similar to the referred to the secondary also. That means the parameters must be transferred from secondary to primary and then primary to secondary. Suppose circuit may be referred as primary is nothing but primary parameters R01, X01 is placed same in primary winding. Now the secondary parameters R02, X02 must be transferred from secondary side to primary side. That may be multiplication of transformation ratio. Similarly, refer to the secondary is nothing but secondary parameters are situated on same secondary winding. Now primary parameters, that is R01 and X01 must be transferred to the secondary. Now combined each, that is R equivalent, R1 equivalent, R2 equivalent, right? Such that we have to draw the equivalent approximation equivalent circuit of a single phase transformer referred to the primary and also referred to the secondary. Now we are going to the next topic, that is voltage regulation, efficiency, and different types of losses, condition for maximum efficiency. Now what is meant by voltage regulation? Generally, regulation is nothing but change in terminal voltage from no load to full load, and it is expressed as a full load voltage or no load voltage. That may be known as voltage regulation of the transformer. Suppose we have to express it with respect to no load voltage, that is nothing but regulation up. Suppose we have to express it with respect to the full load voltage, we can call it as a regulation down. So the regulation generally at no load voltage, some voltage will be available in the transformer. Now we are connecting the load. Whenever you have to put on the load on the transformer, the voltage must be reduced to somewhat. Now change in that no load voltage, that is rated voltage, to full load voltage, that is nothing but load voltage, and it is expressed as no load voltage or full load voltage. That means this may gives the transformer performance, how the transformer may works at no load condition as well as at full load condition. So regulation values may be 0 or positive or negative, and it may be depending upon the load power factor, different types of loads. Already discussed the different types of loads, how we have to draw the phasor diagram for different types of loads, that is resistive load, inductive load, capacitive load in the transformer on load condition. Resistive load, the power factor is unity, voltage and current both are unity in phase to each other. Suppose lagging power factor, current is lagging with some angle pi by voltage. Similarly, leading power factor, current is leading with some angle pi by voltage. So depending upon the load power factor, the voltage regulation may also varies. Suppose if it is unity power factor, the voltage regulation may get positive value. Suppose it may be a lagging power factor, it may also getting positive value. Suppose leading power factor, we are getting the negative value, 0 and also positive value. So this is the most important bit in competition examination and also gate examination point of view. The voltage regulation may varies when it is a leading power factor, that is nothing but positive, negative, 0. Suppose going to the unity and lagging power factor, it may be a only positive. Now let us consider E2 is the secondary terminal voltage at no load condition. V2 is the secondary terminal voltage at full load condition. We have to taken at no load, some voltage is there, and full load, some reduced voltage is there. So we can recognize it that no load voltage is E2 and full load voltage is V2. Therefore, the voltage regulation as per the definition, E2 minus V2 by E2 per unit. Otherwise, percentage regulation, so E2 minus V2 by E2 into 100. As you discussed the performance of a transformer, the voltage regulation value as much as low possible. Whereas in efficiency, as high as possible, then the transformer works efficiently. But coming to the voltage regulation point of view, the voltage regulation of a transformer is as low as possible, that is below 10%. So then we can say that the given transformer may work efficiently. So in percentage regulation, voltage regulation, E2 minus V2 by E2 multiplied by 100. So when all the quantities are referred to the primary side of a transformer, primary side of a transformer is nothing but we know the primary values of a transformer and the secondary values must be transferred to the secondary to primary. That's why we know the only primary values. That's why regulation of a transformer when referred to primary is V1 minus E1 by V1 into 100. For inductive load, E2 is equal to V2 plus I2 R equivalent cos phi 2 plus I2 X equivalent sin phi 2. Where, so this is nothing but plus or minus. Generally, for inductive load, it is a positive value. X contains positive value. For capacitive values, it may be a negative value. For unity power factor, so this term is equal to 0. So now, from this equation, we are getting E2 minus V2. That means difference between the no load voltage and full load voltage. E2 minus V2 is equal to I2 R equivalent cos phi 2 plus I2 X equivalent sin phi 2. And this equation must be remembered, and this equation will be used in the problem when we are solving the problems in a single phase transformer for calculating the regulation. So this equation is very useful. Now regulation, E2 minus V2 by E2 into 100, that is I2 R equivalent by E2 multiplied by 100 cos phi 2 plus I2 X equivalent by E2 multiplied by 100 into sin phi 2, where I2 X equivalent by E2 into 100, that is the percentage resistance drop. Why we are putting this equation? So before slide we are giving the voltage regulation equation, E2 minus V2 is equal to I2 R equivalent cos phi 2 plus I2 X equivalent sin phi 2. That is enough for B.Tech point of view. But going to the competition examination point of view, so they given sometimes percentage resistance drop and percentage reactance drop. So at that time, so you have to just put that values in this equation. We are getting easily voltage regulation. I2 X equivalent by E2 into 100, that is the I2 R equivalent, not X equivalent. I2 R equivalent by E2 into multiplied by 100 equal to percentage resistance drop. Similarly, I2 X equivalent by E2 multiplied by 100 is equal to percentage reactance drop. Therefore, the voltage regulation equal to percentage resistance drop multiplied by cos pi 2 plus percentage reactance drop multiplied by sin pi 2. So this equation may be useful in commutation point of view. So generally regulation is nothing but the former slide equation may be used in B.Tech point of view. Now this equation is also utilized B.Tech point of view as well as computation point of view. Similarly, for resistive load. Resistive load is nothing but power factor is unity, that is cos pi equal to 1. Therefore, sin pi equal to 0, right? So the reactance drop is 0. That means only percentage resistance drop is available. So percentage regulation for resistive load is percentage resistance drop is enough. Suppose going to the capacitive load, so reactance drop is negative. So percentage regulation equal to percentage resistance drop multiplied by cos pi 2 minus percentage reactance drop multiplied by sin pi 2. Simply say that percentage regulation equal to percentage resistance drop cos pi 2 plus or minus percentage reactance drop sin pi 2, where plus is the inductive loads or lagging loads and minus is the capacitive loads are in leading power factors. Now go for the another topic and important topic. They are asking 10 marks sometimes and sometimes they are asking 5 marks also. Losses in a transformer. Generally, any equipment may working continuously, that means more than working hours. It may be 17 hours or 18 hours per day. So the heat may produce in every parts of that equipment. So that heat is in the sense of losses of a transformer or losses of particular equipment. So that losses or heat may be in watts or kilowatts. That's why losses may also considered as a power loss. So that's why the unit for losses is watts or kilowatts or megawatts. So in general, so in first unit or second unit of electrical technology, the rotational losses, that means rotation machines, DC generator or DC motors may having extra losses, that is rotational losses or mechanical losses and friction and windage losses. Mechanical plus friction and windage losses is combined called as rotational losses. But coming to the transformer, that losses are absent. Why? Because it is a static device. There is no rotating parts. That's why the rotational losses are absent in the transformer. The remaining losses is nothing but iron losses and copper losses. First of all, go for the iron or core losses or constant losses. Whenever an AC supply is given to the primary winding of a transformer, that means the primary current is alternating, that may be connected to the number of windings that may develop the MMF, magnetomotive force. Because of that magnetomotive force, an alternating flux is set up in the core. So that due to that alternating flux, hysteresis and eddy current losses occurred in the magnetic core. That means iron losses are occurred in the magnetic core itself. Why iron losses are different? That is nothing but hysteresis and eddy current losses. Means hysteresis losses is nothing but reversal of the magnetization of the magnetic curve. Otherwise, the slope of BH curve will give the hysteresis loss. And eddy current losses is nothing but in the magnetic core. Whenever you are connecting the load in the secondary side, and secondary current will set up the secondary flux, already discussed in the previous classes. Because of that secondary flux, in the primary will set up an extra leakage currents, that is I1 dash. That I1 dash we can call it as extra leakage currents or also called as eddy current losses, that may travel in the primary and secondary winding itself. So that may induce some losses. That losses are called eddy current losses. Iron losses are does not depending upon the load. That's why these losses are also called as constant losses. As load varies, there is no change in the eddy current loss as well as hysteresis losses. As load varies, current varies. Whenever current varies, copper losses are varying, but not iron losses. That's why iron losses are independent of the load and it is also known as constant losses. And hysteresis losses having a empirical formula, WH is equal to eta F V square T square. That means WH is directly proportional to F. Hysteresis losses are directly proportional to the frequency. Therefore, WH is equal to AF. Some textbooks they recognized as pH. Whatever it may be, pH is equal to AF. Similarly, eddy current losses are directly proportional to the frequency square of the frequency. That is, WE is equal to BF square. So by using these two equations, we can calculate the hysteresis and eddy current losses for different frequencies. Go for the other losses and main losses. That is the copper losses. Generally, copper losses are the 30 to 40% of the total losses. So copper losses are mainly occurred in the winding, that is primary winding as well as secondary winding, due to their ohmic resistance. Why? Because whenever the resistance is low, that means the current flowing to that particular winding is high. It may be primary winding or secondary winding. I1, I2 are high, such that the copper losses in the primary winding and secondary winding may be high. Let us consider I1, I2 are the primary and secondary currents, and R1, R2 are the primary and secondary resistance respectively. Therefore, total copper losses is equal to PCU or WCU equal to I1 square R1 plus I2 square R2. Copper losses we can also express it in terms of equivalent resistance, and equivalent resistance refer to the primary, equivalent resistance refer to the secondary. Suppose equivalent resistance refer to the primary, the copper losses are I1 square R01 or R1 equivalent, whatever it may be. Similarly, refer to the secondary, I2 square R02, otherwise R2 equivalent. You can calculate like this also. Otherwise, you can calculate copper losses is equal to I1 square R1 plus I2 square R2. So, as you discussed in before slide, the iron losses are constant because as load varies, iron losses are does not varying with load. That's why iron losses are constant losses. But coming to the copper losses, as load varies, current varies. So current varies means copper losses also varies. That's why. So these losses, that is copper losses, are vary according to the load, and therefore these losses are called variable losses. Next topic, efficiency of a transformer. Generally, efficiency will give the effectiveness of the transformer, how the transformer may work at no load conditions or full load conditions. In total day, how the transformer may working, that may be clearly tells about the efficiency concept. Generally, the efficiency of a transformer is defined as the ratio of output power to the input power. That means output power in kilowatt, input power is also kilowatt. Output power in megawatt, so input power is also megawatt. That means efficiency is a unitless. So transformer efficiency eta equal to output power by input power, that is equal to output power by output power plus losses. That means input is equal to output power plus losses. And it is also expressed as output power by output power plus iron losses plus copper losses. Suppose the efficiency is calculated refer to the secondary. That means we know the secondary values only. That means V2, I2, cos pi 2. Suppose refer to the primary, we know the primary values only, such that we know the values V1, I1, cos pi 1. So by using that values, we can express efficiency of a transformer referred by the secondary is V2, I2, cos pi 2. That is nothing but output power divided by output power is nothing but again V2, I2, cos pi 2 plus iron losses Pi plus copper losses Pc. Suppose you have to calculate the efficiency at full load before slide formula is enough. But now you are calculating the efficiency at any type of load. That means suppose you can consider some x of load, that is x is the fraction of full load. If x equal to 1, that is a full load. If x equal to half, it is a half load. If x equal to 1 by 4, it is a quarter load. If x equal to 3 by 4, it is a 70% of load. So like that, so x is the fraction of the full load. Therefore, can calculate the efficiency at any type of x of load is eta x equal to x into output at full load by x into output at full load plus iron losses plus x square Pc. Why we are putting x square Pc? The copper losses will vary with load. That's why x square. And why we are not putting the x in the Pi is nothing but iron losses are constant. It does not vary with load. That's why you cannot put a term x in the iron losses. So you have to put x square in place of copper losses. Therefore, x into output at full load is equal to x into V2 I2 cos pi 2 by x into V2 I2 cos pi 2 plus Pi plus x square I2 square R equivalent, that is R02. Now we are calculating the condition for maximum efficiency. Any equipment, it may be a transformer or a DC motor or a DC generator, or it may be any other transmission lines, whatever it may be, or distribution lines, to find out the maximum value. That means we have to derivative with the particular parameter, derivate that equation with particular parameter, with respect to particular parameter, and then equating to 0. Now I am taking the efficiency of a transformer refer to the secondary eta equal to V2 I2 cos pi 2 divided by V2 I2 cos pi 2 plus iron losses plus I2 square R equivalent, right? So now, divide the numerator and denominator by I2 such that we are getting V2 cos pi 2 by V2 cos pi 2 plus Pi by I2 plus I2 R equivalent. Now here variable parameter is voltage is not a variable, power factor is not a variable, and iron losses is not a variable. Here variable parameter is nothing but current. As load increases, current also varies. That's why the variable parameter is I2. That's why we have to derive the above equation with respect to current, that is I2, and then equating to 0. We are getting the equation like this. So generally, we are taking the denominator. Why? Because after getting the after differentiating the above equation and then equating to 0 is nothing but, so easily you can d by di2 of denominator equating to 0. So d by di2 of v2 cos pi 2 plus pi by I2 plus I2 are equivalent. So by derivating this equation, so V2 cos pi 2, this is a constant. There is no current term in the first equation. That's why d by di2 of first term is 0. Now coming to the second term, 1 by i2. 1 by i2 of derivative is nothing but minus 1 by i2 square. That is nothing but pi by minus pi by i2 square plus third term i2 r equivalent, that is nothing but r equivalent. So minus pi by i2 square plus r equivalent, that is r02 equal to 0. Then the minus pi by i2 square is shifting the out of the equivalent. So that is pi is equal to I2 square or R02. That means I2 square R02. This is a copper loss occurred in the secondary winding. Pi iron losses. So condition for maximum efficiency is equal to copper losses is equal to iron losses. Otherwise variable losses is equal to constant losses. That means what is the equation gives the, that means you can substitute in iron losses in place of copper losses. Generally A equal to B means put B value in place of A. Similarly, copper losses is equal to iron losses means replace the copper losses with the iron losses for a given efficiency equation, such that we are getting the maximum efficiency equation. So most important for 2 marks and competition wise, whatever it may be, what is the condition for maximum efficiency? That is copper losses is equal to iron losses or variable loss is equal to constant losses. Now we are getting the maximum efficiency curve is nothing but V2I2 cos pi 2 by V2I2 cos pi 2 plus Pi. In place of copper losses, again put Pi. So V2I2 cos pi 2 by V2I2 cos pi 2 plus 2 Pi is the maximum efficiency value of a given transformer, single phase transformer. Suppose at what value of output current the efficiency is maximum? We know the condition for maximum efficiency, that is I2 square R02 equal to Pi. Therefore I2 square is equal to Pi by R02. I2 equal to square root of Pi by R02. So this is the value of output current at which maximum efficiency occurs. Suppose where X is the fraction of the full load kVA at which the efficiency of transformer is maximum. So copper loss is equal to X square Pc. Pc is the full load copper losses and iron losses is Pi. Therefore X square Pc is equal to Pi. Therefore X is equal to square root of Pi by Pc. Now this is the most important. Output kVA corresponding to maximum efficiency equal to X into full load kVA, that is full load kVA into X means square root of Pi by Pc. Therefore, so output kVA corresponding to maximum efficiency equal to full load kVA multiplied by square root of iron losses by copper losses at full load. So by using these expressions, that is load current at maximum efficiency, that is square root of iron losses by R02. At what load maximum efficiency occurs in a transformer is nothing but X is equal to square root of Pi by iron losses by copper losses. At what output kVA the maximum efficiency occurs is nothing but full load kVA multiplied by square root of iron losses by copper loss at full load. So by using these equations, we can find out the efficiency and at what type of parameters we are getting maximum efficiency. That means load current or output kVA, whatever it may be. Thank you one and all. To subscribe, please, to see this video, please subscribe the DBS Talks.